Okay, yeah, so yes, so as I told you, like first we'll discuss some basic linear algebra needed for today's class. Especially we are discussing all this basic linear algebra only solely for SVD. In SVD, suddenly you will be coming across a lot of technical terms. So for that clarity, I'm discussing some basic aspects before it. So make sure you understand each and every aspect. Okay, let's start. Okay. Yeah. So yeah, happened here. Yeah, suddenly it started drawing circles instead of my writings. Rank of a matrix. So what is the rank of a matrix? Of course, you have a matrix. Rank of a matrix says that matrix can be of any size. It can be a rectangular matrix also. So most of the time in this course, we will be dealing with the square matrices mostly. While calculating eigenvalues, I told you, you can compute eigenvalues only for square matrices. You cannot compute eigenvalues for rectangular matrices. But you will be amazed to see that SVD can be applied for any kind. SVD is such powerful. You can apply a singular value decomposition SVD to any matrix, whether it be a square matrix or be a rectangular matrix. So yes, what is the rank of a matrix? So rank of a matrix is definitely a fundamental concept in your linear algebra, which forms the bread and butter of machine learning and AIs. Okay. So what is rank of a matrix? Rank of a matrix is equal to the number of linearly independent rows or numberly linearly independent columns in your matrix. I told you how to the concept. I told you in previous classes the concept about linearly dependent and linearly independent vectors, isn't it? I hope you remember. Yes. Remember? Okay. So just like basic ideas. Just think of basic things. Just don't mug up things. Vectors, and those two are perpendicular. Okay, those two are perpendicular. This is v1, this is v2 vector. Now, are they linearly independent? Are they linearly independent? What do you think? What does linearly independent means? If I ask you to check for linearly dependent or independent, what you do? Can I write one vector in terms of the other vector? Yes. Can you write this j cap, suppose in y-axis and this is I cap? Can you write j cap in terms of I cap or I cap in terms of j cap? You cannot write. Okay, you cannot write. So therefore, these two vectors are linearly independent because you cannot write one vector in terms of the other. Okay. Now let us come to another scenario. You have this vector v1, okay, and you have this vector v2. Do you think you can write one vector in terms of the other? Yes. Why not? And why so? So to understand that, just think of this. In your go back to your class 12th of vectors chapter. Okay, what you do? This is vector v1 and this is vector v2. Of course, there is some angle in between them. I call it theta. There is some angle in between them. And what I do, I just project this vector v1 onto v2. So how I project? It's just a shadow. Don't think of this as technical terms. Think I am putting a light. I am putting a light here, like just this light on this top. So what will happen? This is a stick. Think this vector is a stick. Okay, what will happen? The length of this stick will fall onto this, isn't it? So you will exactly see this shadow, right? How many of you agree? You will see this shadow, right? Yeah, most of them agree. So you'll see this shadow. So this shadow is nothing but the projection of the vector v1 onto v2. Okay with you? Yes. Now what you do? Now you have projected this vector onto this angle, this side, onto v1, and you came to the conclusion that the projected vector is of the size less than that of V2. Agree? This projection is the size is the size is less than that of the V2 vector. Yes. Then what you do? Just multiply till you get vector V2. Just multiply a constant in terms in before that vector till you get the vector V2, because you are in the same direction. Vector is made up of both magnitude and direction. Now you capture the direction once you projected it. The projection of V1 and V2 are in the same direction. Now only thing you need to take care is of the magnitude. How you can take care of the magnitude? You have the liberty of multiplication. Just multiply the scalar. Maybe it is, you don't know how many times, maybe it is 1.5 times the projected ones, or maybe 2 times the projected ones. We don't know. But you just have to multiply the scalar in such a way you reach to this length. So now, what is the takeaway from this idea, like which I just showed? I just told you how you can write V1 in terms of V2. Project it and stretch it. Project it and stretch it, isn't it? That's how you can write V1 in terms of V2 or V2 in terms of V1, vice versa. Yes. So now you came to a conclusion that you can write V1 in terms of V2 and V2 in terms of V1. Okay, write V1 in terms of V2 and V2 in terms of V1. Okay. So what does it mean? It means that V1 and V2 are, because you can write one vector in terms of the other. Okay. So these are two intuitive examples of linearly independent and linearly dependent vectors. When you come across in matrices, come across to matrices, when you come to matrices, what will happen? You have some numbers here, 3, 2, 8, 9, 6, 5, 8, 2, 3, 4. Okay. So you have all these numbers. Now what it means to define a rank for this matrix? What is meant by a rank of a matrix? Rank of A. Rank of A is definitely a number. It is a number. Okay. And as I defined you just now, it is rank of a matrix is equal to the number of linearly independent rows or number of linearly independent columns of the matrix. So here, let us see number of like columns. You can think of these columns as the vectors. You can think columns, the matrix, this matrix A is made up of 1, 2, 3, 4, 5. 5 columns or 5 vectors. Okay, these are the vectors. Now you have to just check whether these are linearly independent or linearly dependent. But yes, that will be very much time consuming. You have to check each vector with respect to each of the other vectors. That's time consuming. So there are some more methods to check or to compute the rank of a matrix. Okay, Python has its own command. You just enter the matrix and type rank bracket A, the matrix name. It will just give you the rank. Okay. Now think rank is equals to the number of linearly independent what do I mean by this? Can you give me what should be the maximum value of a rank from this definition? How many of you are saying 4? How many of you are saying 4? Why? Huh? Number of? No, let me make it even simpler. I understand your issue. Now? Yes. So, how many of you? Maximum. Like, I'm not asking the rank. I'm asking if rank is some number, but what should be the maximum value of that rank? Like can it be the number 19? Can the rank be 19? No. Can the rank be -1? Can the rank be 6, 5, 4, 3? Yeah. So maximum is 5. Okay. So maximum. So rank, the maximum value of rank of A can be equal to the number of rows. The number of rows. Okay. Maximum value it can be. So here the number of rows are 5, 3, 4, 5. So maximum value of the rank can be 5. But we don't know. But we don't know yet what's the rank. Maximum it can attain is 5. Okay. One good way to check the linearly independent or dependent property for this rank is to check for the determinant. Okay. So if you just see the two matrices, suppose you have this matrix. Can you give me the determinant of A? It's a 3 by 3 matrix, so it's a square matrix. Determinant is well defined. How many of you are saying 0? Yes, without even computing, you will say 0 because the two rows are similar. The two rows are just similar. Okay. So you can see that these two are linearly dependent. These two are linearly dependent. Okay. So therefore, computing determinant of a matrix can give you an idea of a rank. Okay. Here the rank cannot be 3. Here the maximum value can be 3, but actual value of the rank cannot be 3 because the two vectors are linearly dependent. Okay, but rank is the number of linearly independent rows. So number of linearly independent rows cannot be 3 here, right? Because the two are already dependent. So it should be less than 3. Okay. So therefore, if you compute, so a method to compute rank, the first step to compute rank of a matrix. The first step, if a matrix is given to you or pops up in your application, wherever you go, and you have a matrix, what's the first step you will do? The first step you will do is to compute the determinant of that matrix. Compute determinant. Okay. Then check if determinant of A equals to 0. If it is equal to 0, definitely this implies that rank of A less than n. That is, n is the number of rows. N is the number of rows. N is equal to the number of rows of the matrix. You got the logic? Got the logic? Here, what is the rank of A? I'm not asking you to compute, but definitely the rank cannot be 3. For this example here, the rank cannot be 3 because these two vectors are linearly dependent. Everyone got this? No? Why? This is, so what is rank? Rank is the number of linearly independent rows. But 468, 468, these are linearly dependent. So therefore, how many linearly independent rows are there? Of course, not 3. Of course, less than 3. Okay. So therefore, I told you about, then rank will not be equal to 3 because rank is the number of linearly independent rows. And number of linearly independent rows of this matrix is definitely not. Yes. If it is not 3, it should be less than 3. Right? If it is not equal to 3, the only possibility is it is less than 3. So this is what I wrote here. Or if you don't like this, then I should write rank of A is not equal to n. Okay. So you have to think also. So the moment I'm speaking, you have to be thinking. Okay. You should not be listening. You should be listening, but you should be thinking also. All right. So check the determinant of A equal to 0 or not. Okay. If it is equal to 0, then you know that rank cannot be equal to the number of rows. It should be definitely less than that. Now, what is the other case? The other case can be determinant of A is not equal to 0, right? It can be equal to 0 or not equal to 0. Equal to 0 we took care of. But if determinant of A is not equal to 0, then it straightforwardly gives you the rank. It straightforwardly gives you the value of the rank. Okay, if determinant of A is not 0, then it straightforwardly gives you the rank. If determinant of A is not equal to 0, what does it mean? It means all the rows are linearly independent, right? No one row can be written in terms of the other. Okay, so therefore, the rank will be equal to the number of linearly independent rows, and the number of linearly independent rows is equal to the n. Yes, you got it. See, when you get determinant equal to 0, when you have linearly independent vectors, this is 468, 468. These are dependent. Therefore, you got the determinant to be 0. If these are totally linearly independent, then you will get determinant non-zero. Yes, got the idea? Yeah, it will take a bit of time to digest. Anyway, but I'm giving you the what you call the basic ideas, so that when you go back and revisit this one, you can actually think, okay. So you can see that when first a matrix is given to you and they are asking you compute the rank of this matrix, what's the first step you should do? Compute the determinant. Compute the determinant. If it is not 0, you are lucky. You are lucky enough, because if it is not 0, rank will straightforwardly be equal to the number of rows of the matrix. Okay, so yeah, and if it is not, if it is equal to 0, if determinant of, there are some vectors inside the matrix which are linearly dependent to other rows of the matrix. Therefore, the number of linearly independent rows will definitely be not equal to n. It will be somewhat less than n, right? I hope you got. Yes. Okay. One best example is the identity matrix. Identity matrix 1 0 0 0 1 0 0 0 1. A 3 by 3 identity matrix. I am asking what is the rank of this matrix? Rank of 5. How many of you are saying 3? How many of you are thinking it should be less than 3? Hmm? Okay. So what is the determinant of 5? What's the first thing you do? Compute the determinant of 5. What is the determinant of this matrix? I. Minus 1. 1. Plus 1. Yes. It is not 0. It is not 0. So rank of I should be equal to the number of rows. Number of rows, because the number of linearly independent rows are 3. So that it is equal to the number of rows. What is, okay? Now I think we'll do an example just that you get a hang of it. Okay, compute this very soon. Okay, so let us take this matrix. To the rank of A. What's the first step you should do? Compute the determinant, right? So compute the determinant and let me know the rank of A. Yes, it should be pretty fast. Okay, so first of all, determinant of A is equal to 6, and that is not equal to 0. So that implies that all three rows of matrix A are linearly independent. Okay, therefore, that implies rank of A should be equal to the number of rows, and that number of rows is 3. Fine. Now let us move to the next example very quick. And I've just made one change. Instead of the 7, I made it 9. Now you compute the rank of it. What do you think? Hmm? Because determinant of A is 0. Okay, that implies that rank of A cannot be equal to 3. It should be less than 3. Okay, if it is less than 3, how to compute? How to compute that? Now, how you will compute rank here? Hmm? Row method. What is that method? Hmm. Yes, yes. So I hope you remembered the row echelon form while computing Ax equals to B. Okay, what is the row echelon form? Form? Try to make the rows 0 as much as possible. Okay, but just not like that, but with the help of other rows. With just help of other rows. Like I can say you an example. Can you do something like R2 row? R2 row can be changed. It can be transformed as follows. R2 row, the second row, is second row minus 4 times the first row. Okay. If you do that, can you do that? And then you can similarly do the third row. Change the third row as third row minus 7 times the first row. You can know why we have this 4 and 7 as per your Gauss elimination ideas and all. Okay, these are the pivots. Hmm? So just do this to the matrix A and let me know what matrix you get. You do this operation, what is your new matrix? And be assured that after you do this row echelon forms, the rank is preserved. Don't think that if you change this matrix, then rank will also change. No. The property is if you do this row operation, change this row echelon forms, rank is preserved. Okay. So after you do these transformations, please let me know what is A1. Mhm. What are you getting? Okay. Okay. Okay, fine. So somewhat we got 2 zeros as from the original matrix. Now we need something more, isn't it? Can you see it? So you can see minus 3 times 2 is minus 6, minus 6 times 2 is minus 12. So second and third row are linearly dependent. Okay. So we can make one more. We can make one more transformation, that is row 3 is equal to row 3 minus times 2 times R2. If you do this, what you get? The new matrix now. It's just similar that the third row will be 0. Yes, you got this. Hmm? Everyone got this? Hmm? Now, yeah, we did all this step, but after that, what? After that, how can we? Our aim is to find rank, but whatever we are doing so far, will it be giving us the rank? Yes, it will. So if you get this, if you reduce the matrix using row echelon form, transform into this row echelon form and reduce it to zeros, then it is a property saying that rank of a matrix that is A is equal to the number of non-zero rows of the row echelon form. So this is the row echelon form we have been doing so far. All these things are the row echelon form we have been doing. So please let me know what is the number of non-zero rows in this final matrix. Non-zero rows. Non-zero rows. Yes. So you can see the rank is now 2. Okay. So rank of A is equals to 2. Of course, it is less than 3, which is the number of rows of the matrix. And more importantly, you can see that the row echelon form of A is it's a special matrix. It's an upper triangular matrix. So upper triangular, what does it mean by upper triangular matrix? Upper triangular matrix means the upper triangular elements will be non-zero. Just remember that. Don't think about lower triangular. Lower triangular will be 0 in that case. Lower triangular matrix means the lower triangular just below the diagonal will be non-zero. Elements will be non-zero. After you do that, above the diagonal, what happens? All are zeros. Okay. So I hope it is okay for you. This example. So at least now you know how to compute the rank of a matrix, right? Fine. So there are other methods. It's fine. I don't, not trying to get it. Okay. So try to explore more other properties of rank by yourself. But this is what you need for this course, I feel. Other properties, if you need, will be told in the due course. Okay. But I feel that this is what you need for now. Okay. Yes. So let's move to a next important matrix. Okay. So now you know how to compute rank of a matrix. You are confident at least. Okay. Confident. Okay. Let's move to a new matrix known as an orthogonal matrix. What is an orthogonal matrix? What is an orthogonal matrix? What is an orthogonal matrix? Anyone heard about orthogonal matrix before? Okay. Let us break down into very simple terms. I feel that many remember orthogonal matrix, but when they are asked about the definition, it is very confusing to them. Okay. So what you can, it is non-trivial. First of all, the definition, the properties of orthogonal matrix are totally non-trivial. It is not that intuitive in mind. Okay. Okay. A square matrix A, I'm telling you the definition. A square matrix A is said to be an orthogonal matrix said to be an orthogonal matrix if transpose of the matrix, that is A transpose, multiply it with the matrix A again, and if you get the result to be the identity matrix, then matrix A is said to be an orthogonal matrix. So a square matrix A is said to be an orthogonal matrix if A transpose A equals to the identity matrix. Fine. So it is a very important matrix because it forms one of the basic elements in your singular value decomposition. Okay. Fine. So if A transpose A equals to I, if A transpose A equals to identity matrix, can we do this scenario that you can multiply A inverse on both sides and get this? How many of you can relate these two statements? Just multiply A inverse on the left side, sorry, on the right side, A inverse on the right side. So A inverse will be identity. The right hand side of the equal to will be just A inverse. So a square matrix A is also said to be orthogonal if transpose of the matrix, if transpose of the matrix A is the same as the inverse of the matrix. So this gives us the another definition. So a square matrix A is said to be orthogonal is said to be an orthogonal matrix if transpose is the same as the inverse of the matrix. So you can see just by doing just a minor change, we reduced two different looking definitions of an orthogonal matrix. Okay. Anyway, so fine. Yes. More importantly, in orthogonal matrix, you will see that it has a property like you can test just by looking into the elements of the matrix whether it is orthogonal or not. How? Orthogonal kind of should remind you of perpendicular things. Okay, it should remind you of perpendicular things. But in this definition so far, we did not see anything related to perpendicular. Okay? So there should be something related to the elements of the matrix. Okay, can you give me a hint? Just think about it. Okay, I will write another definition of orthogonal matrix. Third definition: a square matrix. Okay, a square matrix A is said to be orthogonal. Be an orthogonal matrix. All rows and all columns are orthogonal to each other. We'll check this definition. We'll check this definition. Okay. Maybe some examples first. If I told you this statement right now, okay? If I told you this statement right now, can you tell me how you can deduce this fact? How you can deduce whether this all the rows and all the columns are mutually orthogonal? How you can deduce? Just take the dot product. I told you, if you take the dot product of these two vectors are mutually perpendicular, v1 and v2 are mutually perpendicular, then what is the dot product of them? What is the dot product definition? It is the magnitude of v1, magnitude of v2 times the angle between them. What is the angle between these two? So what should be the value? Yes. Okay. When you're surprised, why? Cos 90 is 0, sin 90, cos 90 is 0. Okay. So if two vectors are mutually perpendicular or orthogonal, the dot product is 0. The dot product is 0. Now, something more is there to this. Orthogonal means it can be having any magnitude. Okay. What do you mean by orthonormal? Orthonormal means the vectors will be of magnitude 1. The vectors will be of magnitude 1. That means these are orthogonal vectors. These are orthogonal vectors of magnitude 1. Got it? So these two vectors v1 and v2 are orthogonal. That is okay. Now, if I tell you, this is the first statement. Now, the second statement is if v2 are equal to 1, that means they are unit vectors, right? They are unit vectors. Unit vectors have magnitude 1. That is the case, then v1 and v2 are orthonormal. Okay. So this is just a tiny change of taste. You can still call orthonormal vectors as orthogonal, but they are something more because they have unit vectors. They are unit vectors. Okay. Fine. So fine till now. Shall we? So I will tell you one property and then we'll look one example. Okay. I'll tell you just one property. Like if you like, just like rank, if I give you a matrix, how can you tell whether it is an orthogonal matrix or not? Okay. Of course, computing through the definition of A transpose A equal to I is one of the ways, but it might be time consuming. It might be time consuming. Okay, because you have to compute the transpose, multiply the big matrices. This method of multiplying A transpose A and getting identity is very hard if the size of the matrix is big. If you have a bigger matrix, how you will do it? Yes. Anyway, I'll tell you one of the properties. So some properties here. Some properties here. Okay. So for an orthogonal matrix, A, you have these properties. So you can make this as test cases. The first statement you can get is every two rows, any two rows and any two columns you take, any two rows of the matrix, okay, any two rows and any two columns, they will be orthogonal. Okay, that means the dot product should be 0. Okay, so every two rows and two columns will have dot product equal to 0. What is the second? I think second is not that essential for now. I think we can discard that. Fine. Only you can take this as the statement. Okay. Now let us consider one example of a matrix and let me know if it is an orthogonal matrix. I'll write down it here. It's a 3 by 3 matrix. Yes. Now can you check, is this an orthogonal matrix? Is A an orthogonal matrix? So what I told you, you can check, take any two rows, take their dot product. Row 1 dot product with row 2. What are you getting? Similarly, you can take any two rows, row 2 dot product with row 3. Or maybe row 1 dot product with row 3. So these are all the combinations you can take, right? So you can take any of them. Even convince yourself that column 1 dot product with column 2, column 1 dot product with column 3, column 2 dot product with column 3. Any two rows or any two columns you can take and check what you're getting. Can you try other cases, other rows, not just one, others? Even eyes tell you, but still. Yes, it should not take too much time. Compute the determinant of this matrix. Like I want to know whether is there any relation with the determinant? If you compute those who have finished computing dot product, compute the determinant of this matrix and tell me what you get the determinant of this. What you get? Hmm? Okay. So what you conclude? Did I pause? No, didn't pause. Okay, what you conclude? Determinant is okay, fine. But before that, let us come. So let me see. What is row 1 dot product with row 2? T. Okay. Dot product with row 3. Okay. Similarly, column 1 dot product with column 2. Okay. 0, I think. So you can conclude that if you want to test for a matrix to be orthogonal, you can take any two rows, any two columns, and their dot product should be 0. Okay, fine. Now, one more thing. Of A is equal to 1. So is it something special that you got determinant to be determinant are usually messy, right? Determinants are usually messy, right? Like they're very complicated. But why they turn out to be so nice, like 1? Hmm? Okay. We came to know about that if A is an orthogonal matrix, if A is orthogonal, then it means that A transpose A is equal to identity, right? Both are square matrices, fine. Both are left side and right side are square matrices. So if I take determinant on both sides, it is well defined. Okay. Is it correct to say determinant of A transpose A is equal to determinant of I? Is it correct to say? Yes, because A transpose and I are both square matrices, and determinant can only be computed for square matrices. Now you must be knowing a property that determinant of product of two matrices is equal to each determinant of the matrix. Is product of the respective determinants. Determinant of AB is equal to determinant of A times determinant of B. So through this, can you say to me that it is equal to determinant of A transpose times determinant of A? Yes. And what is determinant of identity matrix 1? Yes. Now you also know a property of determinant. The determinant of A is the same as determinant of A transpose. You can check it. You can check it. Determinant of A is the same as the determinant of A transpose. So if that is the case, can I write this as determinant of A times determinant of A equals to 1? Yes. Just by using this logic. Fine. Hmm? Okay with you? What does it tell us? Determinant of A squared is equal to 1. What does it mean? It means determinant of A can be plus or minus 1. So now you know why you are getting determinant to be 1. Okay. So orthogonal matrix can have determinant to be plus or minus 1. Okay. Fine. So let us move a quick example. Let us move into a quick example. I'll give you a 2 by 2 matrix. Just by looking, you have to tell me whether it is an orthogonal matrix. Okay. So let us consider this matrix A. Is this an orthogonal matrix? What you do? Since this is a 2 by 2 matrix, you can compute the A transpose. A transpose is what? Then multiply A transpose with A. What you get? Check and let me know if it is an orthogonal matrix. If it is an orthogonal matrix, A transpose A should come out to be last line. Should come out to be huh? Hmm? Yes, identity matrix. So are you getting identity matrix? Hmm? Yes. How many of you are getting identity matrix? What condition did you use? Sin square x plus cos square x equal to 1. That's the basic identity. And compute the determinant also. What is determinant of A? Okay. Can you give me an example of an orthogonal matrix which you just don't need to think about? Just you can just tell me. Can you give me an orthogonal matrix? You don't need to think anything. Like you just can tell me. Like even while waking you up, I'll ask you, give me an orthogonal matrix. You can tell that. Lying on the bed only. Can you give me an example? Yes. Yes. Identity matrix. Can you see the identity matrix? 100010001. This is a 3 by 3 identity matrix. Now I ask you, what is the transpose? What is I transpose? I transpose is the same 100010001. Now what you get? Now if you do I transpose multiplied by I, what you get? Again I. So therefore, this is the simplest example of an orthogonal matrix. Of course, this is, I mean, like the simplest example would be the 2 by 2, but this is the simplest example. Yes. Okay. So we cover the. Okay, just before the break, I want to cover one more aspect, and after that you can go for the break. Okay, and yeah, okay with you? Okay with you for the orthogonal matrix. So till now in today's class, what we learned about? And rank of a matrix. How to compute rank of a matrix, and how to decide if a matrix is orthogonal or not. Okay. Now the next important topic is similar matrices. Okay. What do you mean by that? Similar matrices. Similar matrix. What do you mean by similar matrix? Of course, similar matrix is matrix A alone can be referred to as orthogonal matrix. A matrix A can be told as like A is a symmetric matrix. Okay. But what do you mean by similar matrices? So in terms of similar, you need a pair. You need a pair. You can tell like how Mr. Aman is similar to Mr. Aditya. Yes. How similar they are. Okay. So how similar they are. Then you identify the traits and characteristics. So you can't do just with one matrix. You need a matrix B. So till now we were doing A. Now we need a partner matrix, that is B. So we need to do A and B. We need to say what is meant by matrix A being similar to matrix B. Any ideas? When two matrices are said to be similar? What do you think? What your intuition tells you about? Of course, of course. If you want to compare two, says two quantities, they should be of the same trait. Like Mr. Aman and Mr. Aditya are boys. So I'm comparing along that set of lines. Okay. So if I'll tell that compared to matrices, so that means that they can be of square matrix. Okay. So square matrices, two square matrices, A and B. You can see A and B are both square matrices. Okay. Two square matrices A and B are similar, are said to be similar. Yes, are said to be similar if something happens. And what is that something? Yes, they will also have same eigenvalues. So we'll reveal it. Huh? We'll reveal it. But that is just one criteria. So based on that, we cannot define the similar matrix. Okay. Because if you say same rank, Okay, of course, same rank can be, but it is not the vice versa. If a matrix is similar, then they have same rank. But if they have the same rank, it doesn't mean that they're similar. Okay. So therefore, only based on the rank we cannot classify, or only based on the eigenvalues we cannot classify. There has to be a strong definition to it. And the strong definition is, it is non-intuitive again. It is not intuitive. Okay. It followed from lot of derivations, lot of proofs, lot of theorems and all. So I'll just give you the statement here. So two square matrices are said to be similar if if there exists, okay, if there exists an invertible matrix, if there exists an invertible matrix, which I'll call P, okay, if there exists an invertible matrix P such that something happens, that is P inverse AP is equal to the matrix. Okay. So if I say, and this invertible matrix P cannot be any invertible matrix, it has to be the invertible matrix of the same order. Same order, that is the size of P. Size of P should be the same as size of A or size of B. That means I mean by the number of rows and columns. Okay. Transformation, that is, you see that I had previously a matrix A. Okay, then what I did, like I transformed A. I transformed matrix A into P inverse AP. Such type of transformation, this transformation is usually referred to as similarity transformation. Okay. You do the transformation to check for the similarity of the matrices, and therefore they are known as similarity transformation. Okay, fine. Okay, now there is another notation I would like you to know. If A is similar to B, write this whole line. Instead of this whole line, which I wrote, A is similar to B, you can just write A. So this is a notation. If you want to say A is similar to B, you can just approximation symbol and P. Okay, fine. Let us check one statement. Are you fast enough to compute inverse of a 2 by 2 matrix? Must be knowing a trick to compute 2 by 2 inverse, right? Do you know a trick? Yeah, but there is a trick. You don't have to compute all the things. Anyway, I will leave it to you to explore it. If you have a 2 by 2 matrix, 4 entries, you just have to swap sum and take the negative of that and take 1 by determinant. Okay. Anyway, so we will know now. The question is, take these two matrices. Take these two matrices. A is this and B is this quantity over here. Now I'm asking, check, check. A and B are similar matrices. Check A and B are similar matrices through. Of course, we need an invertible matrix to check it. Through an invertible matrix, through the invertible matrix P, which I am denoting it by, say, 2 minus 2, 2, 2. Can you compute P inverse AP and matrix B and compare these two quantities and reach to a conclusion? What is the conclusion? Compute P inverse AP. If P is this, what is P inverse? I'll wait for you. You have to compute it. Tell me soon. So P inverse AP is equals to B, and therefore you can conclude that A and B, A and okay. Now I give you some more like assignment like things like class assignment that you can check. You can check what is rank of A and what is rank of B. Okay. You can also compute. Well, you can also compute the eigenvalues. Lambda 1, lambda 2 of A and mu1, mu2 eigenvalues of B. And what is the connection between them? Okay. Determinant of A and determinant of B. Okay. So these are just some of the things I want you to compute and make yourself convinced. Make yourself convinced that both are the same. Rank of A is equal to rank of B. Eigenvalues of A equals to eigenvalues of B. Determinant of A equals to determinant of B. And there are many other properties also. Similarly, you can say, you can just here trace. Trace of A equals to trace of B. Just the sum of diagonal elements also. These are some of the properties of being similar. These are the traits of a matrix, of two matrices being similar. Okay. Now let us move to some more properties. If A and B are similar, that means there exists P such that P inverse AP equals to B, right? Now, through this statement, can you say to me that if A and B are similar, that also means that A square and B square are also similar? Can you get this idea? So just I'm just saying that multiply B into B. Multiply B into B. What is B? B is P inverse A times P inverse A. Yes. What you get this P inverse A squared P, isn't it? Why? Because these two guys multiply and give us identity. Yes. So then A into A is A square. Yes. So you can see that B square is equal to P inverse A square P. Matrix P is helping you to determine whether A square and B square are also similar. So you can see how the matrix P is important. Okay. The matrix P, if you find out once, it is going to help you for any power of matrices. Now, similarly, can we take B cube? Can I multiply B square with B? That is B cube, of course. Then B square into B. Can I write it another way? P inverse A square P from above dot B is again P inverse AP, right? Yes. So what you get? Again, these two will multiply to identity. You have this. So B cube is again P inverse A cube P. Okay. So now you can convince yourself that the same will for any integer n, any positive integer, bn, b to the power n, is similar to a power n. So you can see, in fact, a stronger than this is a to the power n and b to the power n, so similar. For any n greater than equal to 1. Okay, for any n. Even n, you can take 200, 1000, 10,000. Okay, fine. Now some properties we have here of similar matrices. The first one is, so rank of two matrices. Rank of two matrices, you just pay the attention here. So rank of two matrices, if two matrices are similar, A and B are similar, then rank of B. Okay. Second, I told you determinant of A is equals to determinant of B. That is the third. Third is the eigenvalues of two similar matrices are the same. That is, you can say, yes, I A equals to I B. That means I'm saying the set of eigenvalues of A is same as the set of eigenvalues of B. Okay, fine. Yes. Say A and A transpose are similar matrices. What do you think? Matrix A and A transpose are similar. Right? No. So wait. So when I am asking that two matrices are similar, don't go directly to the determinant eigenvalues and all. You should check P inverse AP equals to B or not first. I told you if A and B are similar, then these properties are true. It doesn't mean the other way around. It doesn't mean that if determinant of A equal to determinant of B, then you say similar. No. For similarity, you have to check this. Once you get A and B similar, then you can say determinant, rank, eigenvalue, or are same. So I'm saying if A and A transpose are similar. So you can just intuitively you are getting a feeling that, yeah, they're similar. But can you, by using this argument, say that it is the case? Okay, this is an assignment for you. Okay, for the next class. Okay, try to do that. Prove or disprove. Disprove. If you, not necessary that you have to agree. You might disagree also. Anyway, but A is similar to itself, right? A is similar to A. Do you agree to this? A is similar to A. Similar to A. A is similar to A. Like, why? Yes. So what you do? Just take P to be I. P to be the identity matrix. Identity matrix is invertible. So can you say, is it true that A inverse AI is equals to A? Yes. I inverse is I. And you're multiplying everything to I is same quantity A. So it is true. Okay. Fine. Now I am saying you one thing, that if matrix A is similar to matrix B, okay, then matrix B is similar to another matrix C, okay, then this implies that matrix A is similar to matrix. You're getting? That means I'm saying that if Mr. Aman is similar to Mr. Aditya, right? And Mr. Aditya is similar to Mr. last year, Mr. Jubin, then you can say that Mr. Aman is similar to Mr. Jubin. Yes. That way. Okay. So can you tell me why? Maybe this is another assignment. Okay. These are not hard assignments. These are just 3-line assignments. You just have to use your mind. Use your mind in a proper way. Complete these two assignments within 15 minutes. Within 15 minutes. Okay. Okay. I think fine. So wait. Hmm. Okay, so this is what I plan to cover for the first half. This will make you equipped with learning two methods that we'll discuss after the break. That is QR method and singular value decomposition. QR method will be very bit, but I want to give more emphasis to singular value decomposition. It's one of the most important technique you will encounter in every field you go, SVD. Okay, so I will give you both the layman terms of view just by using some colors and everything. and then I will go, after that I will go on to give you a bit more mathematical stuff. Okay, then we'll see an application of image encryption. Yeah, that's it. So